Work it, make it, do it, make sense.
Good morning, everyone. Thank you for being here early, especially if you went to the party last night. It wasn't that easy to wake up this morning, so thanks for being here, and hopefully I can entertain and educate you for 45, 50 minutes or so. So we're going to talk about why I would want a NoSQL or NoSQL database. I will use both terms interchangeably, and about my NoSQL toaster. So my name is Simon Leigh. I'm a solutions engineer at Couchbase. You'll be pleased to hear that this talk is not going to be kind of vendor specific on Couchbase. I'm going to cover the various classes of NoSQL databases. But if you want to get in touch with me, there's my Twitter handle. I'm here on behalf of the Couchbase developer community. Our community manager, Laura, is sat at the back of the room. We have a booth downstairs, so if you want to talk about contributing to the community, or if you want to hear more kind of use cases and sort of the business side of how NoSQL helps businesses, I'll be on the booth with my colleagues and we can talk about that. For now, it's going to be much more sort of theory and the purpose behind these systems. So I always, I think, throughout my career will be asked this question, the relationship between Couchbase and CouchDB. Aside from the acronym Couch, which is a cluster of unreliable commodity hardware, the fact they're both open source and that they had some of the same founders and original developers, they're completely different projects and products. CouchDB is an Apache Foundation project. Couchbase is a sort of sponsored open source project, and Couchbase Inc. company supports it, for whom I work. But they're very different things. So let's take a step back here and talk about SQL being the norm. Everyone, sort of the default choice for databases, people think forever has been an RDBMS. And I kind of use SQL as analogous to saying a relational database system because, of course, it's the language designed to query that kind of database. But let's look at the history of, mankind, but databases in particular. I'm not going to run through from the library at Alexandria, but the first sort of commercial database application was Sabre, which was IBM helping American Airlines to design a booking system. And that's 1960. Interestingly, Sabre is still a company that's running today, one of the global distribution systems. And they are NoSQL users of Couchbase and other technologies, as are Amadeus. So the first application of technology is still very much that company is having to solve similar problems, just instead of sort of 84,000 bookings for flights per day, they're looking at, in the case of Amadeus, 7 million operations per second for people searching flight availability. So the problem in the internet age has scaled. But the relational model, CODS model, proposed in 1970, and then the sort of commercial launch of Oracle only 10 years later. So the necessary sacrifices to the dark gods were made, and Oracle version 1 was released. And even then, after that, SQL Server version 1 is 1989. So it took sort of 30 years from the first commercial database system for SQL to be the norm. And it's since the internet age, really, that other systems were designed. And so CouchDB was written in 2005, but that, in fact, is based on the sort of Lotus Notes model of document storage. So that wasn't even a new idea. Lotus Notes preceded it by many years. And the real explosion of NoSQL technologies came after Google and Amazon's respective academic papers on how do we solve the problem of delivering content and databases to support massive web-scale audiences. So they couldn't keep their relational databases online and functioning well, certainly not without extreme cost implications. And it's always cost, really, from the organization's perspective that affects what technologies are chosen. So Those two papers were published, and then there are a load of open source projects after that. Things like Cassandra, not necessarily open source, DynamoDB, Amazon's sort of public version of Dynamo, React, and all the rest, MongoDB, Couchbase. Couchbase arrived on the scene in 2010, so later than the initial wave. And yes, happy days because they pay my mortgage, so I'm pleased that they came around. But the point here is it took a long time for relational databases to really be the de facto norm. And so even these NoSQL databases have precedents sort of 20 years, 30 years before object databases being around since at least 1988. So this is the key principle of this talk, that NoSQL is not a very useful term, because describing anything by what it is not is sort of necessarily not helpful. A toaster is NoSQL in the sense that I can put data in it in the form of bread. I can get that bread back out as toast, and I don't need a query language in order to interrogate the toaster. But what it is good is marketing shorthand, right? To just distinguish what class of database are you. We're in a broad class, and at least you have a kind of sense for calling them something. So it's worth today talking about the commonalities between NoSQL databases, the various different classes, and how they differ, what are the good use cases at high level, and how these technologies work. So we'll talk about the commonalities. What makes things NoSQL? Is it because of easy development? Not necessarily. As NoSQL databases, we tend to say, developer agility, get things done quickly. But it's not necessarily the case that you don't have to think about it hard beforehand. So they're not necessarily easy to develop for or to operate and scale. The same applies with scalability. With some of them, you have to think carefully about how you're going to achieve scale. Is your data model going to fit the fact that you need to scale out to very high levels? And you can make mistakes. You can choose sort of shard keys wrong. So they're not necessarily all scalable, even though all of them claim to be so, certainly not in an easy manner. The other thing that's often talked about in the context of relational and NoSQL is this acid versus base. So your acid semantic in a relational database versus these concepts of sort of basic availability, soft state, and eventual consistency in NoSQL databases. But there have been NoSQL document databases, and still are some around, which can give you ACID-compliant transactions. Foundation DB was one, and it got bought by Apple, who then snaffled all of their code and took it off GitHub, which was very nice of them. But it's not necessarily that you have to trade off between these two things, because systems are architected in different ways. So still, that's not the sort of common overriding theme of these systems, nor is having schema or being schemaless. Even with something like Cassandra, you do define a schema, even though you may have certain columns in that schema that don't need to be present for every row. But you do still define, a column family with a schema. Yes, with document databases like Couchbase, you have a flexible schema and document model, but they're not all schemaless in a real sense. So I think that denormalization is the most common characteristic insofar as all of these systems share, in order to get their performance, the necessity of denormalizing some of your data, of pre-joining and pre-aggregating things in the model that you store in the database. And you see that across all of the NoSQL databases, regardless of whether they are document, graph, key-value store, or wide column stores. And that's because the problem they're trying to solve is serviced well by denormalizing your data, so you have a data model that tends to be closer to what you need at the presentation tier. So denormalization certainly is the overriding common feature of NoSQL databases and their use. Touch on one last thing with respect to these systems. Yes, they all can use commodity hardware. That's often marketed as a use commodity hardware, I mean in the sense of in your data center, commodity servers, no special appliances, but they don't all have to be on commodity hardware. We have customers using extremely large machines that are not a commodity by most people's standards, and other NoSQL technologies are available on sort of appliances, and Oracle's technology that certainly applies to that. So why would I choose NoSQL for a project? And I would say that if you're starting a new project, don't use a NoSQL database because it's cool, or because you want to pad out your CV, or because there is peer pressure to do so. This actually happens even in the enterprise. You need to consider if the problem you're addressing is solved well by the technology. And if you have lots of experience using a relational database, you're building a small project, you don't want to go for very large scale, you don't need the flexibility of schema, then just use a relational database because you'll be more productive. If you have a problem that does need to consider scaling out to very large volumes of data, or it wants to ingest data and you don't necessarily know about the form of that data at the time of ingestion, so you just write it and then inspect it later, you're saving log files. Things like this are naturally suited to denormalized NoSQL databases, and it's a good place to start. But certainly, and even coming from someone whose ultimate responsibility is to get people to adopt these technologies, I don't want people to put them in the wrong place, because it makes my job harder when I go to a customer and I have to say to them, you've done the wrong thing, now you need to re-architect it. It's better to think about it carefully and make sure you choose them at the right time. So what about if SQL is right? Well, fine. But then we need to think about what the things I need to consider going forward using a relational database. And broadly, scaling can be hard. With any system, scaling is hard, don't get me wrong. Architecting for high loads and high scalability is a difficult problem anyway. And you generally need to introduce things like eventual consistency and sort of event sourcing, message-based architectures as part of scaling to very high sizes. But if you're trying to do it with a relational database, the easiest way is scale the monolith. That also happens to be the most expensive and gets exponentially more expensive as you try and scale one machine, more cores, and you reach hardware limitations. If you're trying to shard relational databases, then you need to think about your sharding scheme. And you can go horribly wrong with that if you make the wrong choices, end up with hotspots. If you need to change it later, doing that maintenance can be costly, require you to set databases to sort of read-only, take databases offline. And so these are the considerations that you should have in mind before you embark on projects using relational technologies and considering using NoSQL technologies. The other thing that is very hard is availability of a system. Availability at all tiers. Availability of my application servers, availability of my messaging technology, availability of my database technology. You have to think about all of these things as needing to be highly available tiers in your architecture. And at one of our previous conferences, at a Couchbase conference in Genico, a payment services provider talked about their architecture. And if you go to kind of microservices talks elsewhere, you will see these tiers appear and using the right sort of tech at each place. And you need to think about availability throughout the whole stack, including the database. And that introduces this concept of CAP, CAP theorem, consistency, availability, and partition tolerance of a system. If a system's running perfectly and nothing's broken, then you don't need to necessarily worry about these letters. If something goes wrong, a network connection breaks, I need to decide, do I want a consistent system, which is also tolerant of partitions of the network, the machines that comprise that system, or do I want a more highly available system, an AP system, so CP or AP, consistent and partition tolerant, or more highly available and partition tolerant. If I choose an AP system, then I'm going to have to deal with the fact that I might have eventual consistency, and I'll talk about what that means shortly. But the theorem dictates that when I build a distributed system, I have to make that choice. I can't have my lunch and eat it. The other thing is that a simple schema for something might be straightforward and easy. Designing these data models can be difficult. Migrating models can be difficult. Anyone who's had to take a database offline to do it, take that application offline, knows that that can be extremely painful. NoSQL tries to mitigate the requirement that you sort of stop the world in order to make changes. Now, you might still need to do that, but sort of the design paradigm is your database should not force you to take your application down. So you should have a database which is available through upgrades, which is available through failures, and that is generally tolerant of maintenance operations without stopping serving that data. And that brings me on to this obviously relevant picture of a blobfish. This is a blobfish, which is a deep sea fish at surface level. And it's not very happy, clearly. But if I show you a picture of it in the natural environment, it looks like a normal fish. It's not a particularly beautiful fish, but it looks like a fish. And this introduces the concept of kind of the right tool for the right job. Polyglot persistence, you could use as the sort of term to describe that. I have multiple different persistence engines, databases, depending on the requirement of the application. And there's lots of sort of literature written on this. But if you've got data that's suited to a relational database, highly transactional, you require ACID semantics, use a relational database. If you want to start storing log data, you want to start ingesting supplier data from APIs where you don't know what the schema is going to be, or it might change rapidly, and you want to be able to ingest that and not have to have lots of work to change your application which ingests it, then use the NoSQL database. So choose the right tool for the right job without exploding within your organization lots and lots of different things, because then it becomes an ops headache. But it's certainly worth considering a balance of these things. All right, so these are the 4 key databases that I'm going to talk about. Document databases, key value stores, columnar stores, and graph stores. And just explain very briefly what they are, how you interface with them, and why you might use them. There is some overlap between all of this stuff, and I'll talk a little bit later on about convergence, but still broadly you can group things into these classes. So, document first. This is a document, not an Excel document, not a PDF, not a Word document, a JSON document in this case, a special class of string, JavaScript object notation, of course, people in this room will be familiar, widely used data interchange format, sort of native support in most languages now, superseded XML because most people don't like XML, as a self-describing interchange format, and also data storage format in the case of document databases. Key points to notice are there's a hierarchical structure, which doesn't exist in relational databases. You can have a list there, and you have sub-documents as well. So that hierarchy is important in being able to model your data. Here is a logo slide of the most common document databases that we see in the wild. Out of interest, and in order to win some swag if you come to the booth later, does anyone know what the logo at the bottom left is? Who said that? That is correct. Yep, okay. Come by the booth afterwards and get some swag. It is Lotus Notes, and I mentioned it earlier, but Lotus Notes was a document database, and CouchDB sort of re-implemented that, open sourced that approach, the replication protocol. It's still in use, strangely, in a variety of organizations, but a nice friendly logo, and worth putting up there just to say none of this is new. In reality, if you're talking open source and what we see at any kind of scale, it's only really 2 of these that we see out there in the wild. RethinkDB, of course, had their own problems as a commercial entity, and it's now sort of taken on as an open source project, and another great technology. Nonetheless, in terms of adoption, Couchbase and MongoDB are the two largest. And they have commonalities between them. JSON being the data storage format. But beyond storing that data, what makes it a database? And if we sort of think about documents in general, Couchbase stores JSON, MarkLogic stores XML, possibly JSON, but in reality, even BSON, which is binary sort of JSON representation MongoDB uses, what we're talking about is JSON. Nice and big, just to reinforce the point. And the document database understands the format of the document, and that's really kind of it. It knows that it's JSON, and it can interrogate it and introspect it. And it can do server-side things, like indexing, querying, reprojecting that data, creating aggregates. Otherwise, it wouldn't be much use as a database. I say this to distinguish it from key-value stores I'll talk about next. Typical abstractions, in this case Couchbase, sort of abstractions, but applicable to other technologies. Buckets, which is analogous to sort of database. Documents, which you could think of as analogous to a row of data in a relational database. Also somewhat like tables in that you get groups of similar types of documents. Views, server-side views that generate indexes on the data using MapReduce. And then for us, NoSQL, query language. For others, Cassandra, SQL. For MongoDB, their query API. So you have features that let you interact with that data. Let's talk about the APIs, since it's a dev conference, how these things, you interact with them. This is a CSV of swag. The product code, the title or the description, and the quantity of that item, very simple. If I want to load that into a document database, I show you an ineligibly small piece of code. But the principle of using this stuff and talking about developer agility and ease of use, to connect to, in this case, Couchbase, I just say create a configuration, point to an IP address, and initialize that connection. Then I connect to a bucket. So it's 4 lines in that method. Very easy to connect to these systems. To load the data, I just read out of the CSV in the first line here, create a record from the CSV for each line, create a document, and associate with that document an ID. So now we're coming back to the sort of key value underpinnings of document databases. Each record has an ID, which is its key, and the value is this anonymous portion called content, which just has the title of the record and its quantity. And then I call insert. And we'll talk about the typical operations on these databases, but it really is just insert the document. And I can then write, out to the console. So very simple to start loading data into these systems, just constructing, in this case, a document per row of the CSV. And this is a screenshot of console and Couchbase. Here's the key of the records and the record itself, which is now a JSON object. Very straightforward, simple document model here. To read this out, I just say, get me the key. So bucket, which is the key space, get me that key, and out comes the record. And I can write each of the elements by using the JavaScript dot notation. This is .NET code, of course. Apologies for that. I know we're all Java fans. And then we write out the information. So very trivially easy to access and write data. And that's why people say, getting started, ease of use for the developer is absolutely up there with these systems. What operations do I use at the lowest level? I upsert data, insert or update it if it's there. I insert it, I update it, I delete it, or I get it, I read it. And that's the lowest level key value access pattern for document databases. Of course, that's a bit blunt. I need to know the key, which only gets me so far. You need to also query a database. So query language. For Couchbase, very simple. Looks like SQL, extended for JSON. And I can just project out items, where clauses. Other databases use different languages or APIs. But very, very familiar interface. Gives me complete flexibility of indexing JSON, which can be very, very useful. If you think of the supplier data example, I ingest that information, and then I might want to interrogate the structure from the supplier. I can do that with the query language. So, last piece on Couchbase, great for devs, scales easily, very fast. If you want to hear more, talk to me later. Here are the key use cases. There are loads of kind of other funky things you can do, but if you're looking at identifying those areas where you might choose this technology over a relational system, where you're not concerned about having the ACID requirements, storing user profiles, indexing user profiles at very high scalability levels, session storage, content management, catalogs. A catalog of products maps, a product maps perfectly as an entity to a single document, and then scaling those catalogs out to service a website, lots of reads per second. Document databases are the best general relational replacement, cover the biggest chunk of use cases, but please don't try and do anything transactional in any of these systems, really, particularly in a document database. Okay, so we talked about document databases, and they're built as key value stores, but what is the difference between the two? The difference is that we still have keys and values, the ID and the value associated with it, but the value here is just anything, a piece of binary data, strings, associative arrays, numbers, anything. And the database or the data store doesn't know about that value. And here is a list of common key value stores. Of course, most people will be familiar with Redis, very popular, DynamoDB, Couchbase can be used the same way, React, key value store. When we, again, look out in the field, if you're using open source technologies, the most common ones that are adopted are these. React are struggling a bit, but still very widely used, particularly in the telecommunications industry. And they split as a class into two distinct areas: in-memory caches, a key value cache, and distributed data stores that are actually built to be distributed. So I'm going to talk about the latter. And this is my point about not caring what the data is. Instead of, in a document database, the piece on the right-hand side being JSON exclusively, you just store whatever you want. And that then means that you have problems trying to index or query that because the database may not know, probably doesn't know what data is being stored. It's just a piece of binary blob. And you'll see that in the React example, and I'll show you the code, which is very similar to that which we saw for Couchbase, you have buckets into which you put data, and you have key value pairs. So, at the top, get a config, create the client, and then with that client, insert an actor. And the actor in this case is an object which is going into the actors bucket. The key is James Bond, and the value is Sean Connery. We're going to be coming back to James Bond shortly to talk about eventual consistency. To get the data out, I just say get, same as with the document database, from the actors bucket, the key James Bond. Very straightforward. And again, that would look like this. I start the system, and then I say, get me James Bond, and I print it to the console. But that's fine for a trivial example. Dun, dun, dun. What about this eventual consistency? And this is about who is the best James Bond. So obviously it's Sean Connery, but some crazy person might say it's Timothy Dalton, which would be unwise, but they might say that. So one application says it's Sean Connery, James Bond is associated with Sean Connery. Another says James Bond is associated with Timothy Dalton. Another one says Roger Moore. Okay, it's fine if my system's all online and I keep writing to that same key. The value gets overwritten. I have one single, strongly consistent copy. If someone trips over a wire in the data center, network fails, something goes wrong, Systems like React choose to have this more highly available system, so it's always available for writes, rather than strongly consistent, which might mean you need to stop taking writes if something goes wrong. So you can conceive of a system, I've got 3 servers, they're all connected together. If I make changes from application servers connected to them, they all resolve to one record. If the network's partitioned between those servers, and one application server writes Ron Connery, one writes Timothy Dalton, one writes Roger Moore, then I have 3 different copies, entries for the same key. And I need to resolve that conflict. So the system, when it's partitioned, when it's sort of in a failure scenario, still accepts the data, but I have 3 different copies. And typically, there can be only one. We have to resolve it. We need to fix it. And highly available AP, key value stores, typically say to the user, the developer, well, you fix it. You work out what happened here. You work out when things were written. You work out which record is the winner. And you need to then set that as the canonical version of James Bond. So there are some things that can help you here. There are sort of conflict-free replicated data types. But a lot of it is pushed back to the developer. And for that reason, AP systems generally are harder to reason about and to develop for than strongly consistent CP systems. And it's a choice over whether you require absolutely no write downtime, but you might have to resolve these issues, or you say I can take 5 seconds of unavailability for writes in my distributed system, my database, but I'm not going to end up with these divergent copies of the same ID. So Couchbase is a CP, consistent and partition tolerant system. That means we have some write downtime for portions of the data. If a server fails, say 5 seconds before the cluster heals itself. Distinct from that, something like React and DynamoDB, they'll accept your write, but you might have to resolve conflicts. So, use cases, highly variable data, I just want to throw it in there, I don't care about it. Caching objects, POJOs, whatever, just serialize them, write them into the store. Session storage, of course, large objects, possibly chunked up across multiple key value pairs, which I can then pull out. And what you tend to want here is very low latency access. Things like Redis, things like Couchbase, sub-millisecond response times, storing complex data types, where you don't need that secondary indexing, that ability to query. Okay, the last sort of general purpose class is columnar data stores. Much more familiar and looks more like a relational database here with a table. They're still kind of built as key value stores where each row is associated with a primary key. The difference here you might notice is that I have a common set of fields, but I have some missing and not nulled, just missing entirely. So a row might have a variable number of columns, none of which are necessarily mandatory. The ones we see out in the field, as per this, the ones that we actually see adopted by the open source community, widely, HBase and Cassandra. And I'm going to focus in on Cassandra because from an operational database perspective, it's the one that you would use. From an analytics perspective, you might choose HBase. And the key sort of things to be aware of here, a key space. So exactly as per any key space, a unique set of keys within a key space. But within that, column families. So this is more like your tables that group related data together. And those column families contain the same set of columns within each family. Each column family has rows and columns. Best illustrated with a picture. Taken from the DataStax website. I give them due credit. This is a blog key space. I know it's a bit blurry, but you have users, you have blog entries, you have sort of a subscribes to relationship mapping column family, subscribers of, and we have time-ordered blogs by user. So notice here that the relationships between the subscriber relationships are handled with their own column family. So you're having kind of foreign keys there, but you need to handle it manually. If I zoom into a column family, or the column families themselves, you can see that these service kind of a grouped purpose, but notice again that in the users, you have name and state possible, but the state column simply isn't in there. And the key to access that row in that column family is the name of the user, just as it is in each column family. But the values associated with the key in each column family are different. So it looks like, in some way, like relational tables, but it's actually laid out very differently and architected very differently. To create key spaces, to create column families, tables, this is how I would do it with CQL. And again, very familiar. But we're saying here we are having a schema enforced here. So this comes back to my point about NoSQL databases aren't necessarily schemaless. Because we are enforcing a schema there and we're choosing primary keys. So the last example, connecting to a cluster, and you're seeing that there are commonalities in how you use these clients. They're distributed, so the application server connects to a host name or an IP address. I create a session, which is connecting from the cluster object to a particular key space, which contains my column families. And then I can execute on that session my queries. I can insert into users, and here you can see that I'm specifying the columns that I'm going to insert. So I need to do that when I write, because all of the columns won't be present for every row. So that's quite a distinction. And I'm associating the values here. Last name was the primary key, so I'm associating those values with each of those entries. And projecting it back out, select star, and I'm giving, in the where clause, the primary key of that row. And just as with the other examples, I can just console write that back out. Bear in mind, in this case, we had also types associated with these entries. In the document databases, we don't have types enforced against the individual fields. So we have a bit more control over that here. But if we want to evolve our data model and move from, for instance, what's one example? Email. Email is a text field, maybe that we wanted to go to a list of emails, and then we want to have an array of things in there. We could evolve that quite easily in a document data model, maybe less so in this data model. So schema flexibility is impaired on the Cassandra side, but from a scalability perspective, Cassandra clusters scale dramatically to thousands of nodes in production at places like Apple in a single cluster. That just shows me what I do when I project that data back out. I mean, trivially easy example, hopefully understandable. So, Cassandra features still something of that impedance mismatch between my presentation layer. I might have to join stuff from across different column families, whereas the document databases we tend to be storing things that are closer to the application level objects, but it scales incredibly well. Can be an ops headache, but there are tools to help you with that. Very well suited to analytics because this data is stored in contiguous rows. So if I talk about the use cases for this, metering data, really large data sets. Smart metering data is one of the classic Cassandra use cases. I collect data on an incremental basis. It's time ordered, it's all arranged in a contiguous rows. So if I want to do range scans and aggregations, I have all that data locality to do it. The document databases, including Couchbase, hash partition your data. So you might have to gather from different machines in order to do an aggregation. Okay, the last type, I won't spend much time on, graph databases. Leonard Euler sort of came up with graph theory, and the problem that he dealt with to design graph theory was, I have these bridges in Königsberg. Can I have a path where I cross each one only once in order to get from, I cross all of them, but I cross each of them only once. And in proving that was actually impossible, he invented graph theory. But if you think about these bridges as relationships between each side of the river, that's what we're dealing with in graph databases. Realistically, Neo4j is the de facto standard for graph, although we'll talk about convergence in the other databases. And here we're storing our entities and relationships. And social networks are the classic use case for graph databases. I'm interested more in the relationships between entities than I am necessarily in the entities themselves. The entity might well be stored in something like Couchbase as a document, and then I store the relationships, the complex relationship stuff in a graph database. But your query requirements are all about how are these two entities related. On LinkedIn, what's your degree of separation from someone else? Who might you be interested in knowing? These are very different class of systems. The typical use cases: social networks, dating sites. Fraud detection is an interesting one. Is the behavior of this person and the relationships that they've established like those of other members of their class? Parcel routing, traveling salesman problem, solving problems like that, going from A to B. What is the relationship between this location, how do I navigate through the nodes to get there? And shopping recommendations, Netflix recommendations, things like that. So those are the four classes of NoSQL databases. There are other specialists, time series databases, things like that, InfluxDB. But broadly, on a general purpose, those are the four that you'll see in the main. But they are converging. I appreciate this doesn't show convergence. It's a damped oscillator, but looks like it's converging. Anyway, systems are converging. You can do graph stuff on top of key value stores because you can model relationships as key value pairs. And if you have a scalable key value store, you can put a graph processing engine on top. Relational databases let you store JSON as a data type, and they let you, to a degree, index that JSON, although it is still seen as somewhat opaque, and the architectures are still table-oriented. But there is a convergence. The query language, like NiQL is an example, it's a superset of SQL. So no longer is there this NoSQL piece. You have query languages for these systems, and the real differences are the underlying architectures. And that's why you should consider the problems that you're trying to solve and whether these systems are suited to the right problem or you're trying to shoehorn use cases onto the wrong platform. So part of that convergence, moving data out to kind of edge nodes, synchronizing your documents out to mobile phones, back and forth. That's what our mobile platform is about, speaking for Couchbase, and syncing that stuff back and forth, having the ability to have a sort of distributed topology and move data through system, route data to the right people, converging sort of the mobile platform into the database. It is the direction that Couchbase has chosen to go, and others might be putting kind of the graph piece on top of Cassandra and things like that. Okay, we talked about all these different things. The pieces to bear in mind is that NoSQL is not useful. There are very distinct classes of system. You should be aware of how your database lays its data out if you're going to choose one of these technologies, of the areas to which they are suited and less suited, and less about sort of grouping these, the four document key value columnar graph into one area, but to say these are distinct things and I need to choose the right one in the right place. So that starts to look like this chart of here's my typical stack where I have web logic and then I have my SQL database. What things look like now is more of the polyglot approach. And these arrows with convergence coming, Elasticsearch, Couchbase, things like MongoDB, Couchbase can do full text search. Elasticsearch is still absolutely the best if you need all the bells and whistles. Attach Elasticsearch. Lots of people are using that in addition to relational and document databases. But breaking apart logic into services, building architectures where these arrows, to an extent, might actually represent a sort of message bus, streaming topologies, things like Kafka, Confluent are downstairs as well, and breaking apart logic into components, having different data stores that handle different things, and having services that own the contract for their own data, ending up with a polyglot persistent system. So one service has its own data store, and it's dedicated to its purpose. And the service owns the contract for how it stores the data, rather than the database backing everything, as in the sort of previous example. Because from here, we can have long-running queries, slow everything down. If we start to break things apart, have dedicated services and systems serving them, then you can achieve very, very scalable architectures. Okay. That is it for the talk. I hope it was really interesting. Couchbase loves developers. Please come and visit us. We're downstairs. We're giving away swag. We're giving away an Amazon Echo Dot at 1:30, but you need to be there to win it. If you want to hear more, blog, Couchbase, developer.couchbase, tweet, go on the forums, go on Stack Overflow, message me, come talk to me. I'm very happy to talk more generally, not just about Couchbase, about what our customers build and about their architectures. I spend 95% of my time not at conferences, but with actual businesses. So if you want to hear about applicable problems and what people are doing, I'm really happy to talk about that and not just talk about Couchbase itself. So thank you very much for listening, and have a good day. Any questions in the room? We have 10 minutes or so.
Did I hear you right in saying that Couchbase was descended from Lotus Notes?
Well, the CouchDB, the sort of model of storing stuff as documents as an objects database and replicating at the document level, is the same paradigm as Lotus Notes. Couchbase's descent is actually from memcached, so in-memory key-value store, and with the document features of CouchDB. So that's where the name comes from. Sort of Membase was the company that supported memcached deployments. Membase plus CouchDB became Couchbase. But certainly the method of arranging data is a descendant of the Lotus Notes approach. Okay. Thank you very much, everyone.